So we will get two vectors. The perpendicular component will be dB sine theta and the horizontal component will be dB cos theta. We are taking a small line element here and we are finding out the small magnetic field due to that small line element. That is why it is small dB. The vertically opposite sides, that is the y components, cancel each other out and there will only be the horizontal components, which is dB cos theta. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about magnetism and moving matter. And in today's session, we will be discussing about what happens to a magnetic field or how we can find out the magnetic field of a current carrying circular loop. So let's dive right into it. So in the previous classes, we discussed how we could find out the current carrying element or the magnetic field at a particular point due to a current carrying element. We found that using Biot-Savart's law and we got the equation dB or B is equal to mu 0 by 4 pi into IDL sine theta divided by r square. Now this was discussed in the previous class and this is nothing but Biot-Savart's law. Now what is interesting here is that this is for a linear current carrying element. Now what will happen if we allow current to be passed through along a loop? That is, if there is a circular loop in which current is passing through, what will be the magnetic field at a particular point P, r distance away from this particular current carrying conductor? That is what we are going to find out in today's class. So is there any difference? Will there be difference in the magnetic field or will there be any difference in the equation? We can find out. So the initial consideration that you have to take into account is that this particular current carrying conductor, that is this particular loop, has current flowing through it which is same. That is the current flowing through is constant. So let's say in this particular direction, current I is flowing through this current carrying conductor which is in a circular loop shape. So if I take a small element, just like in the linear case, if I take a small element which is dl and this particular dl is a vector quantity, so that let's say this is the direction or tangent indicating the direction of that particular vector dl and this is in this particular direction. That is, current is flowing through this particular loop in this particular direction. If we take the small length element here, which is dl, we can say that it has a particular direction which is given by drawing a tangent in that particular section. And this particular tangent will give you the direction of this small length element dl, which is a vector quantity. Now, one thing to be noted is that since this is a two-dimensional picture, this is actually drawn like this. That is, it is actually drawn like this. But in actuality, you must know that if this is the current carrying circular loop, then the direction of the vector dl is coming out like this. That is, if this is the loop, the vector dl is coming out like this and perpendicular to that particular vector dl, r is going like this. Remember, this is not the angle between dl and r. The angle between dl and r is this particular angle. We will be considering that particular angle to be 90 degrees. So just so there is no confusion, this particular angle, that is the angle between vector r and dl, is considered to be 90 degrees in the coming derivation, not the angle between the y-axis and the vector r. A lot of people confuse this particular angle. That is why I am just giving a precaution. So since the precautions are out of the way, let's dive right into the topic. The topic states that if we consider a point P, that is, if we consider a point P right here, which is x distance away from the center of the loop. So this particular point P is x distance away from the center of the loop. And then the radius of this particular loop is nothing but capital R. So we have a circle which is actually a current carrying circular loop. So current is passing through that and this is a circular loop with a radius R. So this particular radius is r. Now what we are going to find out is the magnetic field situated at this particular point, which is x distance away from the center of the circle, and let's call this particular point as P. So our objective is to find out what is the magnetic field experienced at that particular point in time and space, that is at point P, which is x distance away from the center of the circle, which is having a radius of r. We know that from Biot-Savart's law that if we apply Biot-Savart's law, if we consider a small length element right here, let's say this is dl having direction like this, if we consider a small length element dl, then we can use Biot-Savart's law to find out what is the magnetic field at point P. That is, if we know this particular distance, let's call that particular distance as small r. So if we know this particular distance, then we can find out what is the magnetic field at point P. So in order to find that out, certain things has to be understood. The first thing is that since this is a vector quantity, the magnetic field experienced at this particular point, that is at particular point P, that magnetic field will be perpendicular to these two vectors. That is, it will be perpendicular to the vector, the position vector or distance vector r. So these two quantities will be at right angles to each other. So the magnetic field will be perpendicular to the distance vector and the length element dl. So since they are perpendicular to each other, we can say that this particular element, that is this particular magnetic field dB, that particular magnetic field is dB because we are taking a small line element here and we are finding out the small magnetic field due to that small line element. That is why it is small dB. Anyways, we can say that since this particular line and this particular line are at 90-degree angles, that is, since that particular angle is 90 minus alpha, that is this particular angle is 90 minus alpha, we already know that the magnetic field there is perpendicular to the position vector r or the distance vector r. We can say that this particular angle is 90 degrees, which means that the remaining angle, that is the remaining angle here is nothing but alpha. Why? Because one angle is 90 degrees, one angle is 90 minus alpha, because the last angle is just alpha. Because if you add all these together, you should get the total angle to be 180 degrees, because this particular angle is 180 degrees. If you have a line, it should be 180 degrees, no matter how it is cut. So this particular angle is 180 degrees, which means that this angle is alpha, this angle is 90 degrees, which is why this particular angle is 90 minus alpha. So we can consider the angle between the x-axis and the vector dB is alpha, then automatically this particular angle is 90 minus alpha, which means the angle between the y-axis and the position or distance vector r is nothing but alpha. That is how the angles come into play. Now we have figured out the angles also. Now the next thing you have to understand is that here we have x and y components. That is being obtained after resolving dB as the perpendicular and horizontal components. That is, vector dB is being, this is dB. Since this is a vector quantity, we are resolving that into its x component, that is cos component and sine component. So dB sine theta and dB cos theta. We can resolve the vector dB, that is magnetic vector at point P, is being resolved into its perpendicular component, that is perpendicular component sine theta and horizontal component cos theta. That is why there are two arrows like this. It is being resolved into its perpendicular and horizontal component, that is along the y-axis and x-axis, sine theta and cos theta. In order to solve or complete this particular equation, we also need an element dl which is symmetrically opposite. That is, if DL here is coming out like this, then we need a symmetrically opposite element, that is the same element DL, which is going in the opposite direction. So we also need this particular element in order to solve and find out what is the magnetic field at point P. So these are the things you have to keep in mind as I solve this particular derivation. What are the angles, where they came from, which are the notations, how we resolve the vectors, and why there are arrows like that. From the start itself, so there is no doubts. So we are going into the derivation. This is a very important derivation. So we are going into that. Pay attention. So we know according to Biot-Savart's law, we know that the magnetic field dB is equal to, that is, the magnetic field at point P, dB, is equal to mu0 by mu naught divided by 4 pi I dl cross r, that is, these are vector quantities, divided by r cube. That is the vector form, or we can also write it in the scalar form as mu0 by 4 pi I dl sine theta divided by r square. If you want, you can put an r caps here also. But we know this is the vector and this is the scalar terms. To make this derivation easy for you, since I am very generous, I am going to take the sine theta term and make it to 1. That is, sine theta will be equal to 1 when theta is equal to 90 degrees. That is, dl and r, that is the distance vector or position vector r and dl are perpendicular to each other. That is, the angle between dl and position vector r is now taken as 90 degrees. So we can say that I dl sine theta will be equal to IDL because sine theta is equal to 1 as theta is equal to 90 degrees. So we are taking the scalar form from the vector form. This is the vector form, and then we wrote the scalar form. From that scalar form, we are taking the sine theta to be 1 as theta is equal to 90 degrees. So that I am going to write dB is equal to mu naught by 4 pi I dl divided by not r square. What is r square? R square is this particular distance. That is the distance from the element dl to this particular point P. But we don't know what is this particular distance r. We only know this particular distance x and this particular distance r. So we can combine those factors, and using Pythagoras relations, we can say that r is equal to root of x square plus r square, because x square plus r square, base square plus altitude square equals hypotenuse square. So we can write x square plus r square whole raised to 1 by 2, that is root of x square plus r square is equal to small r squared. That is, this particular distance is found out through this particular equation. So we have an equation in this form. Let's say this is 1. So we'll just keep it there. Now we are going to consider the fact that since vector dB is making an angle with the x-axis, that is along this plane, it is making an angle alpha, we are going to resolve that particular vector. Okay, we are going to resolve the vector b or dB into its parallel and perpendicular component. That is x-axis and y-axis, we are going to resolve it. And when we resolve this particular vector, that is when we resolve this particular vector, we will get dB cos theta and dB sin theta. So we will get two vectors. The perpendicular component will be dB sin theta and the horizontal component will be dB cos theta. At this particular instance, we are going to consider the symmetrically opposite line element dl also. because of this particular element dl and this particular element dl, there will be a magnetic field. So we can say that this particular magnetic field experienced will be equal to the resolution, the resultant vector which we obtain after resolving this particular dB. So when we consider the symmetrically opposite line element dl also, then we can say that this particular sign component will be in the opposite direction. So this will be due to this particular line element. The only difference will be that when resolving, the entire thing will be flipped. That is because we are considering a line element which is symmetrically opposite to this, which means only the directions are different in this particular dl. Otherwise, everything is same. The current flowing through this is same as the current flowing through this. And we are going to consider what is the magnetic field dB at this particular point P, which means that this particular resolution will be flipped, which means if I resolve dB for this particular line element also, then I can say that this will be also equal to dB sine theta, and here the cos components add up together and there will be dB cos theta. So which means that the vertically opposite sides, that is the y components, cancel each other out, and there will only be the horizontal components, which is dB cos theta. So we have this particular equation for dB, so we have to multiply cos theta also along that, because dB does not have a vertical component here. I'll explain that much more clearly. That is, dB does not have a vertical component and only horizontal component, means that there is no magnetic field along the vertical plane. Only along the horizontal direction is the magnetic field experience, which means vectorial sense, in vector dynamics, what we can say is that when we are bouncing a ball up and down, it only has a velocity component, or in terms of velocity vector, it only has a vertical motion, which means the horizontal component for this velocity vector is 0. It only has Vy component, that is V sine theta component, as it is only going up and down. The horizontal component, that is Vx factor, will be 0 as there is no vertical velocity. But if you are throwing a ball like this at an angle, like you are throwing a cricket ball, then automatically it has a Vx direction. It will have a velocity along the x direction, that is horizontal direction, and it will have a velocity along the Vy direction, that is the perpendicular component. Here it will be Vx and the height will be due to Vy. So if you're throwing a ball like this, it will have Vx and Vy. If you're dropping it up and down only, it will only have the Vy component. Just like that, here the Vy components cancel each other out as they are opposite to each other. So dB components cancel each other out, dBx components remain. So this particular equation, now we know that there is only magnetic field along the x direction. So we can write this particular equation as dBx cos theta, which means we just have to multiply a cos theta here also. So this is for a small element dB. That is, for a small element dl, the magnetic field is small dB. In order to find out the entire magnetic field due to this current carrying circular loop, we have to integrate that. But in your textbook, it is said that it is being summed up. Both are fine. So we can say that in order to find out B, we have to integrate that. Or you can also use summation. Summation dB will yield you capital B, that is the net magnetic field. So in order to find out the net magnetic field, B will be equal to integral mu naught by 4 pi I dl divided by x square plus r square whole raised to 1 by 2 into cos theta, because it is only the x component that is acting, there is no y component. So we converted this particular term into its scalar form, that is why there is a cos theta here, not sin theta, because the sine components cancel each other out. So we arrive at this particular equation. Now from this, instead of cos theta, we are going to represent that in another sense, that is cos theta is equal to adjacent side divided by hypotenuse. So what is the adjacent side of this particular cos theta? Not cos theta, here it is alpha, so it is cos alpha. Here it is alpha, so we are taking it as alpha also. It does not matter if you are taking alpha, theta, gamma, whatever it is, the theory still holds. So cos alpha is equal to adjacent side by hypotenuse. Adjacent side is nothing but capital R, that is this adjacent side. This is the angle alpha, which means this is the adjacent side, which is capital R, and hypotenuse is nothing but small r. So we can say cos alpha is equal to R by R, capital R by small r. So instead of cos alpha here, I'm going to substitute capital R by small r. Then we can write this particular equation as mu 0 by 4 pi IDL divided by x square plus r square whole raised to 1 by 2 into capital R divided by small r. Now we know that this r is nothing but x square plus r square. So x square plus r square whole raised to 1, because this is entirely one quantity, and here the power is raised to 1 by 2 because it is inside a root. So from here we can multiply these two together, that is the powers will add up. 1 by 2 plus 1 is nothing but 3 by 2. So we can just write it as mu 0 by 4 pi IDL into capital R divided by x square plus r square whole raised to 3 by 2. This is the equation in order to find the capital B, that is the magnetic field experienced at point P due to a current carrying circular loop. But we are not just done yet, because we still have an integral sign here, which means that we have to integrate the varying element. Always remember, even if it is summation, even if it is integration or differentiation, it is always the varying element or varying factor that is what we have to take into account. So here everything is almost not varying except for this small element, which is dl. So dl is the varying element. So what is integral dl? Everything else will come out of the integration sign and we'll have to integrate dl. So what will be integral dl? Integral dl will give you the entire circumference of this particular circle. That is, this particular small element is dl, and if we integrate that, it will give you the entire circumference of this particular circle. That is that current carrying circular loop, and that particular current carrying circular loop has a circumference of 2 pi into its radius, and that particular radius is nothing but capital R. So we can say it is 2 pi R. So instead of dl, we will have 2 pi R, and we can write the final form as mu naught divided by 4 pi I. Instead of dl, we are going to write 2 pi R, or R into 2 pi into R divided by x square plus r square whole raised to 3 by 2. Clear? And then reducing it to even further, we can write mu naught. Here 4 and 2 will cancel to 2, pi and pi will go, r and r will combine together to form r square. So it will be mu 0 by 2 I r square divided by x square plus r square whole raised to 3 by 2. This is the final form of the equation to find out the magnetic field experienced at point P due to a circular current carrying circular loop. So B is equal to mu naught by 2 into I r square divided by x square plus r square whole raised to 3 by 2. That is the final and condensed form of the equation to find out what is the magnetic field because of a current carrying circular loop experienced at a point P r distance away from the circle, or x distance away from the circle. Now we can have a special case, that is, we can have a special case where The current carrying circular loop is this one. And what is the magnetic field experienced at the very center? That is x is equal to 0. Then what will be the magnetic field experience? That is, at this particular special case where I is the current flowing through this particular circular current carrying loop, what will be the magnetic field experienced at the center of the circle, or when x is equal to 0. So when this particular x, that is this particular distance is 0, that is at the center of the circle, what will be the magnetic field? So we already know the equation for the magnetic field, that is equal to mu naught divided by 2 I r square divided by x square, here it is 0, plus r square whole raised to 3 by 2. So x square plus r square whole raised to 3 by 2. So we can write it as mu naught divided by 2 I r square divided by, this will be equal to 2 and 2 will cancel, this is equal to r cube. Now this r and this will cancel out, so we can write this as mu naught divided by 2 into I by r, or simply mu naught I divided by 2r. So this will be the magnetic field experienced at the center of the current carrying circular loop. So this is all about the current carrying circular loop and the magnetic field it experienced. Just remember, this is a very important topic. So you should know how to derive this. I hope you have understood all about deriving the magnetic field due to a current carrying circular loop and what is the magnetic field at the center of that particular loop. I'll see you all again with a fun derivation. Until then, thank you.